Late spring, 2026. Along the equator, in the one stretch of the Pacific that forecasters watch more closely than almost any water on Earth, a number is climbing. It is a temperature reading, and week after week, it keeps coming back higher than the last. For most of the past year, this patch of ocean sat quiet, neither warm nor cold, hovering right at the line scientists use to mark the beginning of an El Niño. Then, sometime in the spring, it crossed that line. And it did not stop. A professor of atmospheric science named Paul Roundy looks at the data. There is a very high probability, he says, that this is the largest El Niño since the 1870s. The last time the Pacific did something like this, the only people who noticed were fishermen on the coast of Peru, watching their nets come up empty. And the strangest part is what the satellites cannot even see, because most of the heat behind this is not on the surface at all. It is already loaded underneath a reservoir of warmth running 6, even 7 degrees above normal, built up quietly beneath the waves, and it has only one direction left to go. To understand what is happening in the Pacific today, you first have to understand what El Niño actually is, and it is not what most people think. It is not a storm. It is not a single event. It is one half of a much larger heartbeat that scientists call the El Niño Southern Oscillation, or simply ENSO. Think of it as the Pacific Ocean breathing, slowly, over the course of years. When the surface water across the equatorial Pacific becomes warmer than average, and the winds that normally blow from east to west grow weaker than normal, that is El Niño, the warm phase, the boy. When the opposite happens, when the water turns cooler and those same winds blow harder, that is La Niña, the cool phase. And the ocean swings between these two states every few years, somewhere between 2 and 7, with quieter, neutral years in between. Now, here is the first thing worth holding on to. This is not rare. This is not new. El Niño has been repeating itself across the Pacific for thousands of years, long before anyone was watching. A typical event develops in the late spring of the Northern Hemisphere, reaches its full strength somewhere between October and February, and then fades on its own, usually within 9 to 12 months. Sometimes it lingers for as long as 2 years, but it always comes back. So, if El Niño is normal, why does the Pacific in 2026 have so many people worried? To answer that, we have to leave the equator for a moment and travel thousands of miles north, to a different part of the same ocean, and to one person who noticed something that, on its own, seemed almost too small to matter. The year is 2013. A scientist named Nicholas Bond is studying the North Pacific. At the time, he holds the title of state climatologist for Washington, which is exactly the kind of job that involves staring at ocean temperature charts that most people would find unbearably boring. And on those charts, he sees something he cannot quite explain. There is a large, roughly circular body of water sitting in the Northeast Pacific. And as autumn turns to winter, that water is supposed to cool down, the way it always does. But it doesn't. It just stays warm, stubbornly, strangely warm, refusing to follow the rules that water in that part of the ocean has followed for as long as anyone has measured it. Bond needed a way to refer to this thing in his writing. So, almost casually, in the monthly newsletter of his own small climate office in June of 2014, he gave it a name. He called it the Blob. He could not have known what he was naming. He could not have known that the Blob would become a recurring character in the story of the Pacific, that it would come back again and again, or that more than a decade later, in 2026, scientists would be watching the ocean for its return with a kind of quiet dread. He just saw a patch of water that wouldn't cool, and he gave it a name. That single observation, a patch of warm water that behaved wrongly, is the thread we are going to follow. Because in 2026, that thread and the ancient rhythm of El Niño appear to be tying themselves together. And no one is entirely sure what happens when they do. So let's come back to the present, to 2026, to what the instruments are actually showing right now. The first signals appeared in the spring. Scientists reported that since April, the Pacific had been behaving unusually, and the trigger, according to the analysis, was something strange in the sky. In the western Pacific, an uncommon pattern formed. 3 cyclones close together, a triple cyclone spinning up over the warm tropical water. These storms generated record-breaking winds blowing from the west. And those winds did 2 things at once. First, they pushed an enormous pool of warm water eastward across the ocean, sliding it along toward the central Pacific like a hand sweeping warmth across a table. Second, they prevented the cold water beneath the surface from rising up to replace it. The cold stayed down, the warmth spread out, and across the entire Pacific, the analysis found warm water sitting roughly 7 degrees Celsius above what is normal. Now, I want to slow down here, because this next fact is the one that genuinely changes how you should read everything that follows. The most important warmth is not the warmth you can see on the surface. It is the warmth hidden underneath. Scientists measuring the water below the equatorial Pacific have found subsurface temperatures running more than 6 degrees Celsius above average. In some readings, closer to 7. A vast, invisible reservoir of heat sitting beneath the surface, out of sight. Let that sit for a moment, because here is what it means. The surface of the ocean can warm and cool quickly. A few sunny days, a few cloudy ones, and it shifts. But the deep ocean is different. The ocean warms and cools much more slowly than the air above it. So when scientists see that much heat built up below the surface, they are not looking at a passing mood. They are looking at a loaded reservoir, a tank of energy that has already been filled, quietly, over months, and that has nowhere to go but up. That is why this matters. The heat is already there. It has already been stored. The question now is simply how much of it will surface and when. And the surface readings have started to answer that question. Through late April and into mid-May, sea surface temperatures in the central eastern equatorial Pacific climbed rapidly, approaching the threshold that marks the beginning of El Niño. The week-to-week numbers in the patch of ocean that forecasters watch most closely surged upward, reaching 0.9 of a degree above normal in the most recent readings. The deeper index of subsurface heat has now risen for 6 straight months. And the atmospheric half of the system, the part scientists track in the air pressure across the Pacific, has begun to fall into line with everything happening in the water. In other words, the ocean and the atmosphere, the 2 halves that have to move together for a true El Niño to form, are starting to lock into step. So what does that mean? It means the boy is coming back. The only real argument now is about how big he will be. To understand why a warm patch of water can reorganize the weather of an entire planet, you have to understand the machinery underneath. So let's build it up, piece by piece. Start with the winds. Across the tropical Pacific, the dominant winds normally blow from east to west, dragging warm surface water along with them and piling it up on the western side of the ocean. As that warm water is pulled away from the eastern side, deeper water has to rise up to replace it. And here is the crucial detail. That deeper water is cold, and it is rich. It carries nutrients up from the dark, feeding the tiny plant-like organisms that everything else in the ocean depends on. This rising of cold, nutrient-heavy water is called upwelling, and it is the engine that makes some of the most productive fishing grounds on Earth. This is why, in a normal year, or better yet, a cool La Niña year, the fishing off the coast of Peru and along the Pacific is good. The cold water rises, the nutrients come up, the food chain switches on. Now, weaken those winds. When the east to west winds slacken, the whole system starts to tip. The warm water that was piled up in the west begins to slide back eastward across the ocean. The upwelling of cold, nutrient-rich water slows down, or shuts off entirely. The cold stays trapped below, and the surface of the central and eastern Pacific warms up and stays warm. That is El Niño. Not a thing that arrives, but a balance that tips over, and the consequences do not stay in the Pacific. This is the part that feels almost impossible the first time you hear it. The temperature of the ocean surface, sitting thousands of miles out along the equator, can change the rain and the snow and the heat over North America. How? The answer is the jet stream, that fast, high river of air that steers weather across the continents. When the tropical Pacific warms during El Niño, it shifts where the jet stream sits and how strong it is. And when you move the jet stream, you move the weather. Storms that would have gone one way now go another. Rain that should have fallen in one place falls somewhere else, or doesn't fall at all. So a warm patch of water near the equator quietly rewrites the seasons for people who will never see that water in their lives. And here is the part that almost feels like a gift. Because the ocean moves so slowly, this enormous planet-spanning system is one of the very few things about future weather that we can actually see coming. The atmosphere is chaotic. It changes its mind in hours. But the ocean takes months to turn, and that sluggishness is exactly what makes it readable. As one oceanographer put it, El Niño and La Niña are the most reliable signals we have for gauging the weather a few seasons ahead. For agriculture, for disaster management, for the insurance industry, she said, there are simply no better indicators. The ocean is slow, and slowness, it turns out, is a kind of warning we can learn to read if we are paying attention. There is one more piece, and it is the most important of all. A strong El Niño does not just rearrange the weather, it releases heat. All that warmth stored in the ocean gets handed up into the atmosphere and spread around the entire world. The planet, briefly, runs a fever. And now, here is something to keep in the back of your mind as we go forward. Remember that the deep ocean warms slowly and cools slowly. Heat that has taken months to build beneath the surface does not simply vanish when the calendar turns. It lingers. It waits. The ocean, in its own way, remembers. Hold that thought. It will matter more than it seems right now. Now we come back to that patch of warm water that wouldn't cool. The blob. Because to understand the fear around 2026, you have to understand what these northern marine heat waves have done before. A marine heat wave is exactly what it sounds like. A stretch of ocean that becomes unusually warm, not for a day, but for weeks, months, sometimes years. They begin near the surface, but they can reach down deep into the water column. And as the planet warms, they are becoming more frequent and more intense. The blob that Nicholas Bond named was the largest the modern Pacific had seen. It was first detected in late 2013 when that circular body of water refused to cool. By the time he coined the name in June of 2014, it had grown into something enormous. It started at roughly 500 miles wide and 300 feet deep. Then it expanded. It stretched to 1,000 miles long and 1,000 miles wide, still 300 feet deep, and eventually hugged the entire coast of North America, from Mexico all the way up to Alaska, spread across more than 2,000 miles of ocean. In places, it ran about 2.5 degrees Celsius warmer than it should have been. A NOAA scientist noted that the North Pacific had not been this warm since people began taking measurements. And here is what that warmth did. Warm water, it turns out, is poor water. It carries far fewer nutrients than the cold water that normally rises along the coast. So when the blob settled in, the base of the food chain began to starve. The tiny organisms that everything depends on thinned out, and the effects climbed upward, link by link. Salmon fled. The Fisheries Science Center in Seattle predicted that catches of coho and Chinook salmon would fall as the fish swam away in search of the food that was no longer there. Along the California coast, thousands of sea lion pups starved, washing up on beaches. In Oregon, thousands of small seabirds called Cassin's auklets starved as well. Warm water creatures appeared in places they had no business being. Thresher sharks and ocean sunfish were spotted far to the north, near Alaska. A skipjack tuna, a a fish of warm tropical seas, turned up off the coast of Alaska, 200 miles north of any previous record. Off Hawaii, biologists watched the first mass coral bleaching event those reefs had ever recorded, and they attributed it to the blob. And over the years that followed, one population of humpback whales was estimated to have fallen by roughly a quarter. The whales pushed toward the coast in a desperate search for food. The ocean, in those years, began to look like a place out of order. Off Alaska, observers found a dead storm petrel, a seabird native to the far side of the Pacific, near northern Asia and Hawaii. Brown boobies, birds of warmer seas, showed up on islands off California. In the spring of 2016, acres of small drifting creatures called by-the-wind sailors washed across the water south of a river delta in Alaska. None of these sightings, on its own, meant disaster, but taken together, they spooked the biologists watching them. Animals were turning up hundreds of miles from where they belonged, in patterns no one had seen before. It looked, to the people who knew the Pacific best, like the entire food web was being quietly rearranged. Like the ocean was sliding its furniture into a new and unfamiliar shape. That is what one warm patch of stubborn water can do. Not through a storm, not through a single dramatic moment. Just by sitting there, refusing to cool, quietly pulling the floor out from under an entire ecosystem. But why did it form at all? And here, even now, the scientists do not fully agree, which is worth paying attention to, because it tells you how young our understanding of this really is. The immediate cause was almost boring in its simplicity. The ocean was losing less heat to the air above it than usual, and the water was circulating less, which left a still, stagnant layer warming at the surface. And the thing holding all of that in place was in the sky. A stubborn, stationary zone of high pressure that parked itself over the northeastern Pacific in the spring of 2014 and refused to move. It earned a nickname of its own. Scientists called it the ridiculously resilient ridge. So that explains how. But it does not explain why. And on the deeper question, the experts split. Some looked at the blob and saw the fingerprint of something much larger and slower, a decades-long swing in the Pacific called the Pacific Decadal Oscillation. A cycle so long that it flips between warm and cool phases over the span of years or decades, and is still so poorly understood that scientists can argue about which phase we are even in. One climatologist believed a cool phase had begun in the late 1990s, and that the blob might be the opening note of the next warm one, with sweeping consequences to follow. Another scientist disagreed entirely, arguing the blob didn't fit that pattern at all, and that the warm water was simply the work of that persistent ridge of high pressure. A third asked outright what caused it, admitted he wasn't sure, but added that there was no doubt this anomaly in the ocean's temperature was deeply meaningful. And then there is the strangest hypothesis of all. One that has nothing to do with the ocean and everything to do with the air over a continent thousands of miles away. When China rolled out a sweeping clean air program in 2013, it stripped pollution out of its skies. That pollution had been scattering and blocking some of the sun's heat. Remove it, and more sunlight reaches the surface. Some researchers have suggested this may have inadvertently nudged the Pacific warmer, though they are careful to stress it was only one factor among many, with greenhouse gases foremost among them. Notice what all of these explanations have in common. None of them is certain. The largest marine heatwave in the modern record appeared, reshaped an ocean, and faded, and the people who study it for a living still cannot fully agree on what summoned it. The blob eventually faded. In 2015, the persistent ridge of high pressure that had been holding it in place finally broke down, and by 2016, the blob was gone, but it did not stay gone for long. In 2019, a weaker version returned, and people braced for it again. This time, a different new detail wrote the ending. A series of storms swept through and stirred the ocean back up, cooling the rising temperatures before they could fully take hold. The the scare passed, and the pattern kept repeating elsewhere. In 2021, a southern blob appeared on the far side of the equator, near New Zealand, reaching out to disturb the weather of Chile and Argentina. The lesson, repeated over and over, is simple. These warm patches are not one-time accidents. They come back, and each time, the ocean shows us a little more of what it is capable of. So now you have both threads, the ancient rhythm of El Niño rising along the equator, and the lineage of the Blob, the northern marine heatwave that keeps returning to the North Pacific. Here is what makes 2026 different from anything that came before. The threads are crossing. Since the end of 2025, an exceptionally large marine heatwave has been forming in the North Pacific. The number being used to describe it is hard to even picture. It stretches across roughly 9,000 miles. There is a band of warm ocean reaching all the way from Papua New Guinea, near the western edge of the Pacific, clear across the water to the coast of California, where temperatures have been running 2 to 3 degrees Celsius above normal for months. And the detail that stops scientists cold is this. The current marine heat wave already covers an even larger area than the original Blob did. The thing that starved sea lions and bleached coral and emptied the fishing grounds. That event is being used as the smaller comparison. Now, layer the two together. In the north, this immense marine heat wave. Along the equator, El Niño conditions emerging at the same time. Together, these warm events are affecting a vast area of the Pacific unlike anything that has been observed before. So, what happens when they meet? Here is where the science becomes genuinely uncertain, and where the careful language matters. Some researchers believe the two events may be feeding each other. As the North Pacific warms, the winds in that region weaken, and that weakening can reach down toward the equator, helping to set up the very conditions an El Niño needs to form. And in turn, the warming at the equator can reach back up and prolong the marine heat wave in the north. A loop, each one strengthening the other. This is not the first time scientists have seen a hint of this. During the original Blob, its second year of extreme warming overlapped with the development of one of the strongest El Niño events ever recorded, which suggested that these large-scale heat events can reinforce one another and stretch the heat out across the Pacific. But in 2026, the overlap is larger, and it is happening from the start. And that has raised a possibility that researchers are putting forward carefully as a concern rather than a certainty. The worry is that this combination could fuel what some scientists informally call a super El Niño, or even a Godzilla El Niño, and that the heat, instead of fading on its schedule, could persist or even intensify across the Pacific well into 2027. I want to be precise here because this is exactly the kind of claim that deserves precision. No one is saying this has happened. The forecasts describe probabilities and possibilities. What the scientists are saying is that the ingredients are present, in unusual quantity, at the same time, across an unusually large stretch of ocean. What they cannot yet say is what the recipe will produce. And there is a quieter reason this matters. One that has nothing to do with the weather forecast and everything to do with the machinery of the ocean itself. Beneath the surface, the ocean runs something scientists call a biological carbon pump. Think of it as a vast conveyor belt. At the sunlit surface, tiny drifting organisms pull carbon out of the system through photosynthesis. And when they die and sink, they carry that carbon down into the deep, where it can stay locked away for hundreds, even thousands of years. It is one of the reasons the ocean is one of the planet's great storehouses of carbon. And the whole conveyor depends on a delicate balance, on cold nutrients rising, on the layers of the ocean mixing, on the microscopic life at the base functioning like a well-oiled machine. Now warm the surface and hold it warm. The machine begins to seize. Warmer surface water is lighter water, and lighter water floats on top, refusing to mix with the cold, nutrient-rich layers below. The ocean becomes stratified, separated into stubborn layers. The nutrients that normally rise to feed the surface stay trapped beneath, and the effects are not evenly shared. Some of the smallest, most opportunistic organisms, including the toxic ones that bloom into harmful algae, can actually thrive in the warmth. The larger life, the plankton and fish and seabirds, struggle. Many ocean creatures can only survive within a narrow band of temperature, so prolonged warming pushes them toward cooler water or down into deeper layers, reshuffling entire food webs. And there is a subtler danger hidden in the timing. Scientists call it a trophic mismatch. Normally, the great blooms of plankton arrive at just the right moment to feed the next generation of fish. But when warming shifts that timing, the bloom and the hungry larvae can fall out of step, the food arriving before or after the mouths that need it, and survival rates collapse up and down the chain. A strong enough warming, sustained long enough, can do something larger still. It can weaken the ocean's very ability to absorb and store carbon dioxide. The storehouse slowly stops storing. This is why the overlap of these two warm events is not just an academic curiosity. To feel the weight of these forecasts, you need a sense of scale. So let's establish what is normal and then look at where 2026 sits against it. An El Niño is declared when the 3-month average temperature of the equatorial Pacific runs more than half a degree Celsius above normal. That's the entry point. The boy has arrived. A strong El Niño is defined as a rise of 1.5 degrees or more. That's already a serious event, the kind that reshapes seasons around the world. And then there is the rarest category, a super El Niño. To earn that name, the key region of the equatorial Pacific has to run at least 2 full degrees above average. In all of the modern record, this has happened only 3 times. Once in 1982 and 1983, once in 1997 and 1998, and once in 2015 and 2016. 3 events. That is the entire club. Now, here is the forecast for 2026. According to the latest outlook from the European Centre for Medium-Range Weather Forecasts, the temperature in the core of the central equatorial Pacific is projected to run as much as 3 degrees Celsius above average by the end of the year. 3 degrees. Sit with that against the numbers we just built. 0.5 degree is the door. 1.5 is strong. 2 is super, a category reached only 3 times in history, and the projection on the table is 3. At that level, forecasters say it would approach, or even surpass, the strongest El Niño events ever recorded, including the Great Event of 1877 and the Super El Niño of 2015. This is why a professor of atmospheric science at the State University of New York described it as having a very high probability of being the largest since the 1870s. And why his institution put it plainly, saying it appears likely, with high confidence, to be the largest El Niño since the 1870s. So that is the ceiling. Now here is the floor of certainty, the part everyone agrees on. The World Meteorological Organization, the world's most authoritative voice on this, has put the likelihood of an El Niño developing in the June to August window at 80%, with the odds of it continuing through at least November at or above 90%. The independent model forecasts go even higher, with one assigning a 98% probability to El Niño through the early summer. The US. Forecasters put the odds at over 80% for an event by midsummer, and 96% that it carries through the heart of the winter. So the existence of El Niño is, at this point, very close to a settled fact. What remains a genuine open question is its strength. And the consequences of that strength reach into nearly every corner of human life. Because a strong El Niño releases ocean heat into the atmosphere and spreads it worldwide, it tends to bring record heat. One climate scientist estimated a roughly 1 in 5 chance that 2026 surpasses 2024, the current hottest year on record, to become the hottest year ever measured, and a 50-50 chance it lands as the second hottest. And if El Niño peaks late in the year, he placed a 73% chance that 2027 becomes the new record holder. There is even concern that this event could permanently push the global average temperature more than 1.5 degrees Celsius above pre-industrial levels, crossing the line that the 2015 Paris Climate Agreement was built to defend. Then there is the food. This is where the abstract becomes a plate of dinner. El Niño tends to bring drought to specific regions, and those regions happen to grow the things the world eats. Forecasters expect reduced monsoon rainfall and a higher chance of extreme heat across central and northern India, the world's largest rice exporter and a major sugar producer. Drought risk rises across parts of Australia, Indonesia, the Philippines, Central America, and northern South America. Indonesia and Malaysia alone account for more than 80% of the world's palm oil. Vietnam and Brazil are the top 2 producers of coffee. The cocoa belt of West Africa sits inside the drought zone. Meanwhile, the opposite problem, heavy rain, threatens Peru, Ecuador, and southern Brazil. One bank's analysis warned that this kind of event could disrupt rice, wheat, and soybeans all at once, and estimated that the number of people exposed to an acute food crisis in 2026 could reach 363 million. The International Monetary Fund has measured how a shock to the El Niño cycle ripples through global commodity prices, raising real inflation by 3.5 to 4 percentage points, and the disasters themselves carry a price. In a single recent year, worldwide economic losses from natural disasters were tallied at $380 billion, only about a third of which was covered by insurance. And the weather does not only take, it rearranges. El Niño tends to push more rain into the southern United States through the cooler months, sometimes enough to cause destructive flooding, even as it dries out the other regions. It tends to suppress the number of hurricanes that form in the Atlantic, while encouraging them in the central and eastern Pacific. It is not simply a switch labeled worse. It is a vast hand that moves the weather from one place to another, leaving flood where there should be calm and drought where there should be rain. There is one more thing that makes the timing of 2026 especially difficult. This El Niño is not arriving into a quiet world. It is layering onto stresses that are already there. Gas prices are already elevated by the war involving Iran. Fuel is costly, and farmers are already struggling with shortages of fertilizer. So the higher food prices that an El Niño tends to bring would not land on an empty table. They would stack on top of pressures the global economy is already straining under. This is why one climate scientist described El Niño as linked to food shortages, water shortages, and even civil wars in tropical countries. It is not just weather. It is, as she put it, something with serious impacts on human society and welfare. The world's official weather body has not stayed quiet about it either. The Secretary-General of the World Meteorological Organization warned that the world needs to prepare for a potentially strong event, one that would worsen drought and heavy rain and raise the risk of heat waves both on land and in the ocean. She pointed out that the most recent El Niño, the one spanning 2023 and 2024, was among the 5 strongest ever recorded, and that it played a role in the record-shattering global temperatures of 2024. Extreme heat, she noted, is already one of the deadliest hazards we face. A strong El Niño could sharpen it, spreading heat-related illness, widening the range of disease-carrying insects, and pressing harder on food and water. Communities that were already struggling, she said, would be pushed even further past their limits. And the head of the United Nations put it in starker terms still, warning that El Niño was arriving on the world's doorstep with 90% certainty, and that it would pour fuel on the fire of an already warming world. Its impacts, he said, would hit harder, travel farther, and cross borders with devastating speed. So, after all of that, after the probabilities and the projections and the long lists of consequences, you might expect a clean conclusion, a verdict. There isn't one. And the honesty about that is, in a way, the most important part of the whole story. Because here is what the careful scientists keep returning to. Yes, El Niño is almost certainly forming. The probability is now near 90%, but its peak strength is still genuinely uncertain. The US forecasters have been blunt about it. In their assessment, no single strength category, not weak, not moderate, not strong, has reached even a 37% chance of being the outcome. The strongest El Niño events in history are the ones where the ocean and the atmosphere stay tightly coupled all through the summer, and it simply remains to be seen whether that happens in 2026. Some models point toward a record. Others do not predict a strong event at all. This is what real science looks like in the middle of an unfolding event. Not certainty, not a headline. A room full of careful people watching the numbers come in, week by week, updating their odds, and refusing to claim more than the data will allow. The next formal discussion of the conditions is scheduled, like all the ones before it, for a specific day on the calendar, after which the watching simply continues. But step back from the week to week, and there is a larger thought that some researchers have begun to put forward, quietly, as a possibility rather than a fact. Remember the thing I asked you to hold on to, the idea that the deep ocean warms slowly and cools slowly, that heat once stored does not simply leave. Now, place it next to what we are seeing in 2026, a marine heat wave larger than the Blob in the north, an El Niño rising at the equator, the two of them overlapping, possibly feeding each other, possibly stretching the heat out past this year and into the next. What if these overlaps are not a coincidence? That is the unsettling possibility on the table. That the Pacific Ocean may be entering a new kind of era, one in which these climate extremes increasingly overlap, reinforce one another, and last longer than anything we have measured before. Not single events that arrive and fade, but events that pile onto each other, the way the Blob's second year once piled onto a record El Niño, only now as the rule instead of the exception. We named this thing 200 years ago when a fisherman pulled up an empty net and a warm current arrived at Christmas. We have spent the centuries since then building satellites and floats and models to watch it, to measure it, to give it categories and probabilities and thresholds. And we have gotten remarkably good at it. We can now say, with real confidence, that the boy is returning, and roughly when. But notice what all of that watching has actually revealed. Not control, not even full understanding. The more closely we look at the Pacific, the more we find that it is doing things we have never seen before, on a scale we have no comparison for, driven by machinery we are only beginning to map. We built the instruments and pointed them at the largest ocean on Earth, and what they showed us, in the end, was the size of our own ignorance. For now, the heat is already in the water. The reservoir beneath the surface is already full. And all we can really do is what that fisherman did 200 years ago, standing on the coast with his empty net, watch the water, and wait to see what it has decided to do.